purpose of today's lesson is to look at how different units of measure exist for particular situations, but why some are more appropriate than others. So we just want to talk about a couple of common things here for a moment. If you think of a very common distance that might be used every day, so in my example, being a baseball fan, it's 90 feet between the bases in a Major League Baseball field. Well, that's an appropriate unit of measure. I really wouldn't want to convert 90 feet into a unit of inches and figure out and describe the distance between the bases as 1,080 inches, nor would I want to convert it into miles and indicate that it's point something miles. It just doesn't make any sense. So you'll see in everyday life that certain units of measure are preferable over others. To just go through a couple of examples on that. For instance, the dimensions of a dining room table are given as 3.5 by 5 square feet. Well, it's probably not too crazy to say that that's also 42 by 60 square inches. Still something that people can relate to. But I wouldn't want to convert that into its mile equivalent because that's going to be a very small number and not of any use to me. As a second example, a MP3 player allows you to play your digital recording library. And let's say you have 1,000 songs, or it can hold 1,000 songs, and on average that's 4 minutes. Well, obviously that means it can store 4,000 minutes of music. Well, that's nice, but let's look at other units of time measure and see which ones are relevant. Well, seconds, that would be 240,000 seconds. That doesn't really do much for me. If I were to convert it to hours, I can see that that's 66 2/3 hours. That's pretty good, not bad. Days, it's approximately 2.8 days to play it all. And then weeks becomes 0.4 weeks. The point of this is that when you convert it to a unit of measure that's a reasonable number, either not too large or too small, then that's of more use for practical purposes. So in this example, 4,000 minutes isn't bad. Seconds clearly doesn't do me any good. Weeks really doesn't make sense to convert it there. Hours or days, probably a little bit more appropriate. The third example here, we're making cupcakes, and each cupcake takes 20 grams of sugar, and you need to do 500 of them for a school bake sale. That's a lot of cupcakes. So that would take 10,000 grams of sugar. Well, the number 10,000, not the most unreasonable number, but still not as useful. What would be more useful? To convert this into pounds. So if 1 pound is equal to 453.59 grams, I can figure out the pound equivalent. You can set up a proportion of 1 pound to 453.59 is the same as X, my unknown pounds, over 10,000. And when you do your cross multiplying in that, what you end up doing at the end of the day is dividing your 10,000 by 453. Because there's more grams than there are pounds, so for 10,000, my number should be smaller. I'm going to divide, and I'm going to get approximately 22 pounds. Definitely a much more reasonable number to work with. Now, if we go back to some numbers we had previously used, we had come up with the mass of a proton and electron as some very, very small number. And you should know that they're very small numbers because the exponents are very small and negative. Okay? Now, if I wanted to convert these kilograms to grams, and I know 1 kilogram is 1,000 grams, I would multiply each one of these by 1,000, and I'll show you it for one of them. Well, we know 1,000 is equal to 10 to the third power. So I'm just multiplying this string out. And when I multiply with same base, I'm going to add the exponents. So I just convert or change my exponent of negative 27 when I add 3 to it to negative 24. So in grams, it's this number. Well, that really doesn't do me much good because it's still a very, very small number. So what has happened in science is that particle physicists have come up with their own unit of mass called a giga-electron volt. And 1 giga-electron volt is equal to 1.783 times 10 to the negative 27. And the reason is that they want to take these very, very small numbers, and instead of giving them to you in grams or kilograms, they're going to convert them into giga-electron volts. And the way to think of how to do this conversion, and I'm going to do the proton here, and then the electron on the other side. But if you think about what you're trying to do is you're trying to figure out how many giga-electron volts one proton, the mass of one proton is. So I want to know what number times 1.783 times 10 to the negative 27 is equal to, and let me get rid of this so I can have a little bit more room, 1.672622 times 10 to the negative 27th. Well, I want to know how many giga-electron volts it takes, okay, to convert over the mass of one proton. I'm going to divide both sides. And when you do that, you obviously would be doing this with a calculator. You're going to get 0.938. Since you subtract the exponents, these are going to cancel out to 10 to the 0 power. Anything to the 0 power is 1. So the mass of a proton is equivalent to 0.938 giga-electron volts. Okay? And it kind of makes a little bit of logical sense because you're going to see, if you look at it, they have the same base 10 and exponent, but since 1.67 is a little smaller than 1.783, you're going to be just under 1 giga-electron volt. Now, if I do the same thing for the electron, again, the electron has an exponent of negative 28. So that's going to be smaller, okay? So when you do your division, you should see that 9.109382291 times 10 to the negative 28. Again, dividing by the determined value of a giga-electron volt. Keep saying that fast, it'll drive you crazy. Okay, that is approximately 5.109 times 10 to the negative first, which in standard form would be 0.5109 giga-electron volt. Okay. Now, a similar situation, and you saw this in the video on Friday, is dealing with very far distances. And looking at the next example, what scientists have come up with, and you should be familiar with this term, is light years, because they know the distance, say, from the sun to its nearest star, Proxima Centauri, or the star 61 Cygni, are very, very far distances. So instead of saying or describing their distance in actual kilometers with some large exponent, they've come up with light years. And this is the formula for light year. 1 light year is 9.46073 times 10 to the 12th kilometers. So now, instead of saying how far Proxima Centauri is in actual kilometers, we're going to convert its distance into light years. Now, you should see that this distance is greater than 1 light year because it's 10 to the 13th power. So you should be expecting a number, okay, and that's 12, that should be 13. You should be expecting a number greater than 1 because the distance from the sun to Proxima Centauri is greater than 1 light year since it's a larger number. Okay, so I do my division. Again, you would be using a calculator to do this. You get 0.4241 times 10, which is 10 to the first, which then means the distance is a little more than 4 light years. Okay. If I do the same thing for the other star, again, 61, I'm going to divide its distance. Now you'll see that this should be even more light years of distance because it's 10 to the 14th power. And when you do that, you'll get 0.11403 times 10 squared. I really want to put that in standard form because I can relate to 11.403 light years. Okay. So again, what the point of today's lesson was, first we discussed the different ways of units of measure for distances or weights or time, and what's more appropriate than the other. But the crux of it was to identify specific areas in science where scientists have come up with a different unit of measure because the units that they're dealing with are either very large or very small numbers.